Bon, mais bonjour à tous, bienvenue pour ce web séminaire donné dans le cadre des web séminaires du réseau Plasma 3. Donc ce séminaire a lieu aujourd'hui depuis de la place et on a la chance d'accueillir Tomas Hoder. Donc le web séminaire durera environ 50 minutes, une heure. Suite au séminaire, vous aurez la possibilité de poser des questions. Alors soit en direct, soit via la fenêtre de chat Zoom. So Tomas Hoder is associate professor at the Masaryk University, Brno, in Czech Republic. Tomas.
Thank you. Thank you, Nicola, for the introduction. Yes, I will talk about ultra-fast plasma processes in gas and liquid environment today, and just very shortly, I will introduce my institution. I'm from the Department of Physical Electronics in Brno, Masaryk University in Czechia. The department is approximately 70 academics and researchers and 30 PhD students. Is divided to several groups and working on different topics from plasma physics to plasma different plasma application. I'm with the group of plasma diagnostics and modeling. And I would like to talk today about the ultra-fast plasma processes. And of course, from my point of view, it is connected to experimental investigation, to diagnostics of such a plasmas and of such a processes, such a mechanisms on very short time scale, using dominantly quantitative optical emission spectroscopy. Well, so first for the gaseous environment, I will try to establish some link between the theory and the experiment and diagnostics, of course. So if we look at the time scales for plasma physics in a gaseous environment, of course there is a huge span over the time scale from the resulting chemical equilibrium after several seconds back down over the shock waves and heating and radical chemistry to some electron collisional processes at the very beginning. These are actually the processes, and these time scales between up to few units of nanoseconds are the timescales I will be talking about. At the beginning, also about the equilibration of the relaxation of the electron energy distribution function, so we can actually apply some quantitative spectroscopy. So if you look what is the case for ultrafast, what is the source for the ultrafast plasma processes? Of course, it is driven by two possible mechanisms, by rapidly changing voltage pulses. So we have some externally applied changes in the electric field, or we can have also changes in rapid changes in the electric field due to some inherent discharge mechanism, for example, the streamer mechanism. If we look just to give some special cases, some examples for very short voltage pulses. You can see here, probably this is experiment by Tarasenko and his group, as introduced in the review by Nidis. We have voltage pulses from 0 to minus 200 kilovolts at less than 1 nanosecond, and at the same time generation of super short avalanche electron beams, non-local electrons which are hardly in the equilibrium. And this is one, let's say, more extreme case. Another interesting case is I can speak about the recent experiments done in Greifswald, where with similar time scales we're able to measure here using the streak camera the development of the ionization or the radiation from the plasma really within a few hundreds of picoseconds, and we're able to follow it using some fluid modeling. Also a very fast process with photoionization in the gap, and including some streamer like ionization waves spreading through the volume afterwards, already in pre-ionized gas. Well, and finally we have the streamer mechanism. Very shortly to introduce the streamer mechanism is basically resulting from, let's say, accumulation of space charges by electron multiplication. Fast, in our case, it could be a fast avalanching process leading to localized positive charge density increase, and then with that resulting self-enhanced electric field in that location, and propagation of the streamer head driven by secondary avalanches and photoionization. These are events very short. On the current recordings, the isolated streamer, you can have a milliampere pulses with nanosecond time scales, and at atmospheric pressure air, as I will be talking dominantly about such a condition at the beginning, we have really few tens of microns the spatial scale for these discharges. So we have a really fast and really tiny discharges, and it is of course challenging for any plasma diagnostics. Well, I show you the source of the electric field, the fast changing electric fields, which can actually drive the electrons, which are then reacting in the gas. And from this point of view, the local field approximation for, say, hydrodynamic description of the streamer phenomena is, of course, typically used for glow discharges or Townsend discharges in atmospheric pressure already, where the time scales are really slow in microsecond, but is also very much applied to the streamer discharge phenomena with, I would say, great success, and being able to describe really the basic the physics of these discharges. Of course, there are exceptions for very high fields for streamers in contact with surface, and you can here see, for example, the deviation between the fluid and the hybrid modeling for such discharges, where there are non-local electrons which are for this, even for these cases, are however just a small part of the electron gas, which is not local, and as a result, the dominant part of the phenomena can be very much described in the hydrodynamic approximation. So why it is important for us for the diagnostics whether there is a local field approximation or not? Because optical emission spectroscopy, especially some quantitative description, relative description between two different wavelengths, different emission from different radiative states, is based on the collision radiative model, which are actually without a dimension, and as such actually rely on the local properties where we are taking from local coordinates. So especially for streamer discharges, their erratic appearance in time and also in space, it is sometimes, or their propagation close to the surfaces, it is very complicated to of course, it's possible under special condition, but it's very complicated to analyze them or to diagnose them with a laser spectroscopy. Also at atmospheric pressure air, as I said, the diameter of these discharges at the range of tens of microns, so any length on where the laser can interact with such a discharge is really limited on these microscopic dimensions. So actually the optical emission spectroscopy gives us the opportunity to really get, using some magnifying optics, for example, to get some local properties about the discharges and to get some local, well-resolved information. The important things is, of course, we use a time-dependent collision radiative model for such analysis, of course, for some relaxing plasmas or for long-term glow discharge, thousand discharges. There's no need usually to use this term, time-dependent term, in the collision radiative modeling. But for such a rapidly changing plasma as I'm talking about, of course, this is a crucial. As I said, we have then access to the local properties. We can establish time-dependent models for collision for radiative states. Here, for example, the case for the first negative and second positive system of molecular nitrogen, which is given by these two states, and we can actually, of course, this is a result of the fluid model. We can then, for instance, quantify the development of the emission at the streamer head and follow all this information, let's say, in fluid. And then if we are able to record such a properties of such a discharges with high resolution, we can also follow it on the spectra and compare it in some detailed way. We have, of course, if we apply fluid model, we can also then reconstruct or synthesize the spectra for such a discharge. If we simulated also the densities of radiative states, and we can actually resolve the optical emission spectra according to this very short and small distances, and to have a really good overview about the emission from the streamer discharge. As in the streamer discharge, the dominant part of the emissions coming from the streamer head. Also, for some quantitative analysis of such a discharges, as I said, we need the local field approximation, as it is used for the collision radiative model. But the question arises: and are those electrons under such a high field application are local? Is there the sufficiently fast and short relaxation of the electron energy distribution function present or not? So one of the possibilities is, of course, to plot the momentum dissipation frequencies and energy dissipation frequencies for a given gas, for given conditions, and the energy dissipation length and mean free path for our conditions, and compare them with some typical time scales of the electric field change under the same conditions. And of course, if the frequencies for the momentum dissipation and energy dissipation are much faster than any actually observable change in the electric field or for a given discharge, then we can pretty much, based on this very easy and I would say fast estimation, say that okay, there is a local field approximation. Or we can do some more complicated things to compute the temporal relaxation of the electron energy distribution function, and see that for, let's say, these cases, we can see the relaxed distribution functions from the solution of the Boltzmann equation, or from the Monte Carlo simulation of the series 1000 experiment, and you can see the spatial relaxation of these the distribution function. We can say, of course, it's possible. It was done by many, and under this condition, we can say that for these fields, for our the relaxation times at the scale of tenths of picoseconds, and the spatial relaxed intervals are at units of microns. So actually, for our case, for streamer discharges, also for the resolution of any possible device, it is quite well prepared. So now the question arises how to record the emission from such a discharge. Of course, there's many methods how to use it, and many tricks how to go into the details. One of them is, for example, the sub-nanosecond gated ICCD cameras. Today, they are broadly available, typically also around 200 picoseconds, which is, of course, not very good, but using some extension of the gating from 200 picoseconds to 210, 220, you can simply step by step add your time step and subtract the previous one, and get a relatively nice overview, two-dimensional, about the emission of the discharge. Another thing are fast photomultipliers. You can get nice profiles of the emission from the discharge, but for example, for the two-dimensional description of or two-dimensional measurements, as it was done here for lower pressure air, some additional data processing is necessary in order to get some well-prepared data for further quantification, for further analysis, for example. Of course, there are also streak cameras, which have the advantage that we can make a single shot measurements for some very intense discharges, but usually at the very stages the emission is not so strong, so you need to accumulate anyway for the very first hundreds of picoseconds of such a discharge. So the other problem arises is the proper triggering to the discharge. So the discharge is not jittering with respect to your applied gate, and so on. So, but for certain condition, it could be also done. The other method is what can be used is, for example, the time-correlated single photon counting-based optical emission spectroscopy, where you actually solve the triggering problem or the jittering between the recordings and recording and the discharge itself. That every let's say step in this procedure, you count single photons. Every photon you detect is correlated directly to the discharge itself, so you have no problem with any triggering issues. You have high temporal resolution, high signal to noise ratio, and actually the only problem is that you can apply it for very high frequency discharges, let's say about 5 kilohertz. It makes sense, and the problem is, of course, and if you want to study some discharges in not without pre-ionization, this is of course the problem for you. So we have the possibilities how to record signals, and of course we would like to link the experiment, or to prepare the experiment for such a discharges, in this case the streamer discharges, in as many detail as you can. One of the possibilities is to use, for example, the analytic model for streamers developed by Kulikovsky and following Naidis, which are very useful for diagnostic of such a discharges, especially if you have, for example, no access to some complex modeling, and these analytical models are relatively well checked for given conditions by numerical models. And it starts, let's say, with the proposal of the, let's say, simplified shape of the electric field in the streamer head, which was proposed by Kulikovsky and was checked by his numerical simulation. The question, of course, is whether it is also like that in the experiment, and there are two cases where you could observe such a behavior in the experiment. For example, for lower pressure air, the streamer in barrier discharges, the red dotted line is actually the measurements, and the black line is the fit using the model of Kulikovsky. So you see it is very well present. The same thing for streamers in helium plasma jet, where they could be really described by this simplified analytical model. So it gives us already some good start, some solid link between the simplified theory and the experiment. And of course, I will not go too much into detail, but using all this equation and combining and can result, for example, in the quantification of the time lag between the peak emissions of from two radiative states excited in the streamer head. So, for example, if you want to compare, really for your further analysis, the emission from let's say different radiative states, you need to have a well-established relation between them. You have to know where the maximum will be, and this should be shown also in the experiment. So this is one of the possibilities how to really relate some detailed analytical understanding to the experimental setup. So if you plot the results, in this case it is made by the black lines. If you plot the results of, let's say, delay of the emission from the second positive system in the streamer head behind the electric field, because of course first we have the electric field which passes the coordinate, and after that we get a rise of the emission, and for different radiative states with different excitation thresholds, we have different delays in the peak emission of such a radiative different delays for peak emission. And you can actually look whether your experiment is able to follow such a fast changes and distinguish between the lags of these two emitting between these two emissions. So after that, you if you somehow establish the link, if you can if you see the coherent results of these comparisons, one can really apply some quantitative approaches to study the plasma experimentally. And one of them, for example, is to probe the electron energy distribution function for two energies and get some results for example, changing electric field, because we have a fast discharges. So dominantly we have emission from the radiative states which are populated by direct electron impact, and we can based on the thresholds for this radiative states, we can actually trace the electron energies for given times. So, for example, as the field is rising in the discharge, at the beginning, let's say we have a radiative state for the second positive system, which has threshold at about 11 electron volts, and the first negative system, direct electron impact excitation, where we have threshold about 19 electron volts. And as the field rises, the shape of the distribution function changing, and as you can see, the ratio of these two contribution to the optical emission is also changing. So this is actually very nice signature, which I mean, this is nice, very nice and useful way how to find a changing signature in the optical emission from the discharge, if resolved, of course, with high temporal resolution. Very shortly, as I said, we have direct electron excitation for second positive system with 11 electron volts, for first negative with 18 or 19 approximately electron volts. We include all the important processes for a given case, and it results in two differential equation. We can divide them, and as a result, we have on the left side something what we can measure. These are the intensities and their temporal changes. Here is the importance of the non-steady state or time-dependent kinetic model, and some let's say values for a quenching, which can be also taken from the experiments or theoretical. It depends. On the right side, we have a dependency of the ratio, let's say defined ratio of the intensities of this ratio of the emission intensity from these two states, depending strongly on the electric field. And if we can link it to the experiment, we have then evolution in the we can plot the evolution in the electric field. Of course, to get the proper so-called calibration curve between the intensity ratio and the electric field is a not easy task, and of course it will be probably a topic for another talk. But just briefly, necessary to show that the processes included are really only those which are necessary for the description of the system. So you can do some sensitivity analysis of the model, uncertainty quantification. You can look into the different quenching coefficient. So the really selection of the proper constant is very crucial in this case, which gives then the uncertainty for such a curve. And of course, there is an influence of spatial temporal resolution. I mean, in evaluating, for example, here the measured data, and influence of the temperature and so on. Well, so here I guess I've tried somehow to link the really very fast and first processes in the gaseous environment to some quantitative optical emission spectroscopy, and I will continue to the second part of my talk, and it will be about ultrafast phenomena in liquid environment. And again, I will try to construct some link or some picture-based, not only on theory and not only experiment, but somehow in common. So if we start, of course, the pulse or the breakdown in liquids is studied already for a very long time, and it was very at the beginning found that for very short pulses there is something different happening. For longer pulses, let's say above 1 microsecond, it was clear that there is a vaporization of the liquid media in direct vicinity of, let's say, the electrodes, and we have actually, as a result, breakdown then directly in the bubbles and not in liquid media. But with the improvement of the fast switches and high voltage pulses, there were more and more possibilities to study it at nanosecond or even sub-nanosecond time scales of the applied voltage. Of course, there were rise time, sub-nanosecond rise time, and so on, applied to the sharp electrodes in liquids. I will talk about water dominantly. So it was a possibility really to dig a little deeper. And the question arises: okay, how are the electrons multiplied, or what is the mechanism for such a discharge in liquids? One of the models is based on the field ionization rates, as it was, for example, modeled by Sun. In this case, it in supercritical nitrogen, of course, in some special conditions, and it was also followed also proposed by some other groups. In this case, we can see the proposed mechanism based on the electron tunneling from the electrode and in the volume as proposed by von Keudel. And we can see the link of the development of the optical emission spectra to the proposed model. So we have at the very beginning the field emitted electrons at the electrode, and with the time we have a heating of the electrode, which can be visible as interpreted as a black body radiation, and with another component which is coming from the hotspot generation and further electron emission from the cathode as observed. I mean, as interpreted by the spectra. They were also able to compute or to estimate the electron densities based on such a model, and this was, of course, the proposal of the optical emission spectra analysis by thermal black body radiation was also proposed earlier. The question then arises how it can propagate further in the liquid, and there is another possibility, to electron tunneling detachment from OH radical, or from electron tunneling from water molecules, which seems up to now as one of the very promising candidate for the ionization in the water further from the electrodes. But all these models, or the Zener-based model, didn't account for the possible changes in the water itself, in its movement under the electrostatic force and so on. And very interesting model was proposed earlier, that if we apply very sharp high voltage pulses to the to sharp electrodes, the highly non-uniform electric fields will lead to formation of nanoscopic voids, or such a nano ruptures in the liquid media, which are actually not proper bubbles. There are no gas inside, no vapor. It's simply just a disintegration of the liquid matter itself, and it takes place. It results from the volumetric electrostatic forces, and it can follow to cavitation to this voids. And of course, if we have at least several tens of nanometers long voids, we have enough space for electrons to be traveling with, and to get the energy from the surrounding field, and to ionize inside these nanovoids further to contribute to the ionization. If you look in the equations, you can see that we can describe the electrostatic force-based pressure. We can, of course, we need to describe also the dynamics of the water by equations for continuity of mass and momentum. And if we plot it for these conditions, we can say for two cases of 3 nanosecond rise time or 100 nanosecond rise time, that the total pressure, this is the red curve for 3 nanosecond rise time, is going below -30 megapascals, which is the threshold for cavitation in water. So actually, at the very close area around the tip, let's say up to 40 microns there is a possibility to create actually the nanoruptures or the nanovoids in the media. While for the 100 nanosecond rise time, you can see that the red total pressure is not going over or under the threshold, and as such, there is no actually possibility to create such a void, such a ruptures. So that means that we actually have some space for the electrons to get energy for ionization. And if we then say, okay, we have the condition for cavitation, and we wait for, based on some stochastic effects in the liquid, to some small some inhomogeneity in the water density, and we can actually say, let's say there are some initial discontinuities of 2 nanometer, let's say, diameter. We can then again introduce the pressure on the surface of such a inhomogeneity to the balance for kinetic energy, to the equation which is describing balance of the kinetic energy of the expanding fluid and the forces responsible for the pressure on it. And we have then condition how the actually nanovoid can expand or collapse. And if we look to on the result here, and we see that actually for the distance 1 micrometer from the electrode, we have again for these conditions, we have grow of these nanovoids up to 16 or 18 nanometers. And if we recompute this with the electric field in these nanoruptures for the electron energy, the electrons can get a 10 electron volt energy within these small distances, within these nanometric scales, and are able to ionize, let's say, surrounding water, as the ionization potential of the water is about 10 electron volts. So what we see that there is a possibility that there is a space in the water created by the electrostatic force, and there is also a possibility that some primary electrons, of course we don't know where they are coming from, possibly from the OH radical tunneling or detachment, and we see that there is a possibility to have such a let's say interpretation of the very first moments for the discharge in a liquid media. And if we look at the spectra, optical emission spectra from such a very fast events, you can see here the spectrum for 100 kilovolt pulse on a 50 micrometer curvature needle in the water. And if you increase the gate from 250 picosecond to 500 picosecond to 1 and 3 nanosecond, you can see actually, here is a better visible, you can see a propagation, of course, in the spectral range, in the wavelength scale of such a wave from higher wavelengths toward shorter wavelengths and getting more and more intensive. Very similar spectra was observed for different conditions also by others. As I said, here it was interpreted like changing blackbody radiation coming from 2 sources. But the emission, the continuous emission in such a discharges can be also described as a electron neutral Bremsstrahlung. And if we use such an approach, of course, at the very first stages, we have no, and if very small contribution from electron ion Bremsstrahlung, because there is nothing ionized yet. So the main source for such a possible electron neutral for such a Bremsstrahlung emission is from the electron neutral interaction. And if we take into account a Maxwell-Boltzmann energy distribution for the electrons, we can see that this is actually not working. It cannot be described by such a approach. As you can see, the points are the measured spectra, the continuum radiation in the spectra, and the lines are the fit. So let's try to fit such a curve for a distribution function that it is fitting the spectra. And in such a shape is the bell shape electron energy distribution function, which is actually a beam-like distribution function for electrons. And if you apply it to the emission coefficient for the electron neutral Bremsstrahlung, the final intensity is very well in agreement with the spectra. So what we have actually are electrons, a beam of electrons which are continuously accelerated within the nanovolts, and we are talking about 2 and 3 electron volts. So this very well in the energetic interval, as I was saying before, in the nanoscopic dimensions. And a very interesting fact is that such a bell-shaped electron energy distribution function is typically observed for field-emitted electrons. So this fit of the experimental data give us some hints also about the origin of the very primary electrons. And that was the last slide from my presentation. So of course the phenomena of the plasma, ultrafast plasma phenomena or discharge phenomena in the liquid environment is very intensively studied. Only as you could see within the last 1 year, there is plenty of very important, or for me at least, very interesting papers which are somehow describing different mechanisms with good evidence, and there is still a lot of questions. And I guess we can expect some very nice papers soon as well, because this is very interesting part of the, I would say, of the research in cold plasmas. So thank you very much for your attention.
Thank you, Thomas, for your presentation. So now we have time for discussion. In the Laplace, but also from people in Zoom. Who wants to ask the first question? I will cut this part for putting everything online.
And there is. Okay.
I am not familiar with the plasma in liquid, and you said it, I think, but I didn't get it. What is precisely a nanovoid? How can you define the nanovoid?
Nanovoid is due to the pressure, negative pressure resulting from the electrostatic force. You have decrease in the density, and suddenly, because the liquid is not really homogeneous media at these scales, under the threshold of this minus 30 megapascals, you can actually produce really ruptures, nanoscopic spaces between, let's say, the surrounding water molecules. So this is actually not a bubble. It is not some kind of structure with surface tension, probably I don't know. Let's say this is actually it is for the discussion, but there's not a vapor style bubble within the liquid. So there is simulation. There were really some particle simulation of generation of such a nanovoids. I guess it's, let's say, 6 years ago. Very much also where they really were able to produce a very long, thin, such a cigars-like shapes, which were branching, and due to the stochasticity of the media and under such a extreme conditions, it's actually really it's really interesting. So, but
what is the media side of the voids?
I would say there is a vacuum, time to time, some molecules, water. It's a very small. It's a few nanometers. It's you could the time scale, the spatial scale is very, very, very short.
We have a question from Svetlana. Svetlana, you can turn on.
Yeah, can you hear me?
Yes.
Yes.
Cool. Thank you very much for so nice talk. It was very interesting, and I will be very interested to have all the publications which follow this talk. I was really very much interested by this changing of spectra and going of the spectra to more and more ultraviolet region with time on sub-nanosecond time. And my first question is related to this modeling of the spectra, because it's fantastically interesting. The question is, you take into account the Planck and Bremsstraße emission, but do you take into account emission CW also, which appears because of recombination? Because already at this stage, you should have high density of excited species, and recombination rate in liquid should be very high.
Oh, well, I'm not sure. I mean, the recombination is not taken into account, and the point is actually we are at the very beginning. These are let's say, from the point of view of the hypothesis, it was presented. These are very first electrons. So I don't think there is much excited or ionized, even ionized particles, so it's very, very beginning.
I see. Okay. The second, if possible, 3 questions. Okay, Nicolas?
Yes, of course.
Thank you. The second question is about, and the second and the third questions are about the first part of your story. The question number 2 is the following. Actually, in any streamer or in any non-zero D experimental object, you have radiations of 2 different lines coming from different points. And for sure, it's some convolution of electric field and of the electron density at this point. When you say that, okay, we have electron energy distribution function, and we have unambiguous relation between emission and EEDF or electron energy, that's true for 0D situation.
And
how do you solve this?
It is true for 0D, and it is also true if you have enough high resolution in time and space. So you can, for example, resolve these different, let's say, parts of the discharge where the emission comes from. So of course it could be used as I said. I showed you also before let's say the analytical model and the experiment for the development of the emission and the lags between the emission of different states and the electric field. This is something which is actually on time scales of tens of picoseconds. And given the fact that actually the whole field and the discharges are on much longer time scales from this point of view, hundreds of picoseconds. This is some of the area, and you are right. This is the very crucial part of such a diagnostics. You have simply be able spatially and temporally to resolve different parts of the discharge in order to be okay with the zero dimension for the given point. So that's
I
true.
see. So everything is in the hands of experimentalists. And the very last question:
No,
what do you do if quenching is not only due to bath gas like oxygen or nitrogen? What do you do if there are collisions of excited species with electrons, with other excited species, with atoms, etc., which is not so unusual feature in the well-constructed discharges with the diameter of 10 microns or 20 or 30 microns?
I'm not sure about this. Certainly, I mean, validating or digging deeper into the kinetics for this model, we colleagues made sensitivity analysis where complete model for air was included, even I guess with all these reactions you mentioned, and for electron densities up to I guess power of 10, power of 12 per centimeter, it was not it was negligible, the contribution.
Okay.
So
thank you very much.
I'm not sure about the numbers now, but for streamer it should be okay.
Thank you very much.
You're welcome.
We have a question also from David Pai.
Can you hear me?
Yes.
Okay. Thanks, Tomas, for a very, very clear and thorough seminar on two pretty different topics, and for presenting a lot of the current work on this stuff. And I have one, I guess, sort of question-ish remark followed by a question, if that's okay. Is that okay, Nicola?
Yes.
So the remark, I guess, is what both of them concern the water breakdown. And when you talk about these little nano voids, I guess it reminds me a little bit about breakdown in supercritical fluids near the critical point, which I guess is a more obscure topic than the breakdown of liquids that you're describing, but near the critical point of a liquid, well, it's not a liquid, it's supercritical fluid. The thought is that there are such voids being created, and they're rather dynamic, and they might be of the same size scale as these electrostriction generated voids that you're talking about. And I don't know if you have any thoughts on that, or if there have been comparisons, or is it appropriate, the comparison between these two types of breakdown mechanisms? And I guess that leads to my question about the modeling that you did, which was very interesting. That beam electrons, when you apply them to the electron neutral Bremsstrahlung model, ends up fitting pretty well to the experiments. And but there's something I guess I don't understand, is that I guess the void that you're talking about, there's I guess nothing in the void, and the model for the Bremsstrahlung, as far as I know, is based upon sort of a gas phase radiation model. And so my question would be, what is if the electron is being sent into the void in a beam fashion, what is it colliding with in order to generate this radiation? Is it colliding with the wall of the void? And in that case, it's colliding with a liquid phase environment. And does that radiation model extend to like a liquid wall?
Yeah, the hypothesis is pretty much that. So it is actually the collision or the flyby the wall. And but it should not be forgotten that this is not really a void. This is not a big. This is really units of nanometers.
Okay.
It is really really small, and I guess the further, let's say, expansion of this hypothesis of these nanovoids, of this electron propagation through these nanovoids in a later phases was pretty much well, I mean, very nicely described by my colleague Zdeněk Bonaventura in paper also 3 months ago. So it's a very interesting phenomenon, but I'm not sure whether I can give you some more answer. No.
Okay, but you suspect that it's the radiation is resulting from a collision with a liquid phase, right? And
with the molecules in the surrounding space. Yeah.
Oh, okay. And so I guess the question I'm asking is related to the spectral model itself. Does the model apply just as well to a liquid phase collision as a gas phase collision? Is it a general model, or is it?
I'm from I look here.
Because I would expect the. I guess I would expect the because the binding.
There are some. I'm not sure now anymore. There are some simplification we made. But at this moment, I'm not sure I would reply.
Okay.
Sufficient detail. So.
Okay. Thank you.
Yeah, you're welcome.
Thank you, David. We have another question from Marie-Agnès.
Yeah, thanks a lot, Nicolas. And again, congratulations to Thomas for this impressive talk. It's not really at the beginning, if you can understand. So my question is in the continuation of David on a very particular point. So you're mentioning very extreme, fast transformation and extreme conditions at a very nano scale. Have you any idea about the formation of solid phases under these extreme conditions? And have you any collaboration with, in fact, other teams working on the synthesis of solid phases from these extreme processes? Thank you.
Thank you for the question, but probably I will disappoint you. I'm not. My work is really connected more to the diagnostics of the discharges and not to some production of some solid phase materials. But there are, of course, reports of a possibility to produce really interesting materials in such a media, especially a high. Yeah, in a high and fast electrical pulses to liquid media of different kind. I know about liquid nitrogen, and so it's very interesting, but unfortunately I'm not the right guy to reply.
Thank you.
Other question? No. Okay, so thanks again, Thomas. Thank you for this very nice talk.
Thank you for the invitation.
You're welcome. Et à bientôt pour un prochain web séminaire du réseau Plasma Froid.